Hello everyone and welcome back. Now we are going to talk about how the GPU driver is modeled in MGPU sim. So here we show a figure of how the different components in organize an MGPU sim. On the CPU side of the simulator, we have the GPU driver and the IOMMU. These communicate through a network of root complex and device switch, which is PCI model, and communicates to the GPU side. In the GPU side, the central communication point is the command processor. The command processor is actually responsible for handling requests from the GPU driver. Now, in terms of the compute unit, which is a GPU core, it receives work groups or work from the asynchronous compute engine, which is the dispatcher. Then it translates virtual address to physical addresses through a network of TLBs and IOMMU. And then caches are addressed physically here. So in terms of the L1 vector cache, for example, is addressed physically. And then in any cache miss is served by the lower levels of memory hierarchy. So the driver API actually provides an interface for the application or the main program, which is written in Go, to communicate with the GPU. It handles all different other tasks, such as memory allocation and movement, as well as kernel launching. Command queues are present in a driver that are responsible for translating commands to requests. And then the driver would send this request to GPUs. And on the GPU, the command processor is actually responsible for handling this request and then doing the appropriate work. The important thing to note here is that the driver actually runs on the CPU, and we do not model the driver execution latency. However, we do model the driver to GPU communication, which happens through the PCI in fabric. Now, driver API is very important as it simplifies the hardware to software co-design. This is very similar, in fact, to OpenCL and other programs. So it provides an OpenCL runtime API, for example. It provides a similar API to write the host programs in Go. Some of the important things here are, for example, how do we initialize in context? So in our driver API, we provide a function called driver.init. Then in terms of memory management, we have different functionalities. For example, for allocating memory, we have simple allocate memory. Then we have API calls for copying memory from host to device and device to host. So as you can see, these are very similar to what the runtime API calls that typical GPU programming frameworks provide. Now, in terms of how the kernel is launched, we need to prepare a structure as to how the different fields are arranged. So these fields need to be in order. What that means is that in the main kernel or the actual kernel, how the arguments are arranged, these arguments need to be in a similar order. So one important thing to note is that the fields need to be aligned, and this is something that is part of how the GPU kernel actually works, or how the compiler actually recognizes these things. And then, so there needs to be some sort of padding. And then another important part to note here is that this driver.gpu pointer are basically 8-byte unsigned integers that points to array or can be anything. So this is something that that you need to keep in mind when writing a new benchmark for execution in our simulator. And then these arguments are actually passed to the driver.launch kernel function, which is what is actually responsible for sending the kernel to the GPU and launching work. As you can see, it contains very familiar arguments. For example, the grid size, the thread block size, and so on. So overall, these APIs provide an easy way for a user of MGPU sim to write their own benchmark host program in Go, and then use a kernel to launch the simulations in MGPU sim. And we'll take you through an example of how this is done with an example of one benchmark. In terms of the API, again, there's another things like, for example, command queues which are provided. So these command queues are similar to the OpenCL command queues. The default command queue is actually blocking. However, we can create our own queues using the driver API calls again. For example, the create queue, we can drain the queues using drain or drain all queues. Similar to OpenCL queued APIs, we also provide queued APIs such as enqueue memory copy H2D, which is similar to the OpenCL enqueue memory copies. So overall, the simulator driver API is trying to provide a similar sort of runtime API as the OpenCL runtime. In the future, we do plan to support a full-fledged OpenCL or HSA runtime. However, for the meantime, we use the driver API to write the host program in Go and then use it in our simulator. Another important thing to note is a very recent addition to our simulator is the concurrent workload execution. So there are two different forms of concurrent workload execution model that is supported by our simulator. So when writing the main host program in Go, if we have two benchmarks and these two benchmarks use different GPUs, then the driver will schedule them accordingly. For example, if benchmark 1 uses GPU 1 and 2, and benchmark 2 uses GPU 3 and 4 in a multi-GPU system, then the driver would schedule them accordingly on the different GPUs. So in that case, if we are talking about contention, the only contention would be for the CPU side service from the IOMMU. On the other hand, if we want to study concurrent workload execution on the same GPU, then we can basically have these two benchmarks. We can have a main Go program where we initialize those two benchmarks and then select only a single GPU on them. So then what would happen is that these two workloads would again run on the same GPU. So this is very interesting scenarios, as a lot of prior research has shown, for example, supporting these forms of concurrent kernels. And as a result, we model them in our current simulator. In the next section, we are going to take a look at how to prepare a benchmark for mGPU sync using the driver APIs that we just discussed.